Thanks, Susanna. It's kind of false advertising to say that I'm going to talk about the whole complex ore bodies program. Mainly what I'm going to talk about is my stuff, the bits that I was involved in. I'm not proposing to, there are quite a few people in the audience who are actually working on aspects. I'm going to give an overview at the end of the talk about the various things that are going on in the complex ore bodies program, but I'm not going to present any detail on work being carried out by some of the other programs that I haven't been involved in. But what I do want to talk about is some work that we set out to do very early in the program, really because of the nature of the program. As Susanna said, the whole idea behind this program, and I'll sort of develop this a bit more later, was that with the growth or the continued growth of demand in the future, and the decline of new discoveries, and the unlikelihood that recycling is going to meet that demand, there's a whole, resource of undeveloped ore bodies, but also unexpanded ore bodies, if you'd like to say, that are held up for various reasons that aren't just technical. So that's kind of what we were saying at the start of this program, but what we didn't actually know was whether that was true or not, and to what extent that was true. So what I really want to talk about is the work, mainly the work that's been done along those lines in the last little while, and then I'll come to with that, I guess, underpinning behind us, to then talk about some of the things that we've been working on that try to address the issues that came out of that initial analysis. Whoops, we're not actually on the slideshow yet. Help if I did that. Okay. So a lot of our early work was done on copper, but I've expanded that with working with other people to a lot of other commodities as well. But Richard Shoddy from Minex Consulting has done a lot of work putting out information relating to copper. And what this basically shows is a graph of production and resources as we understood them in 2010. And that was that cumulative production and loss basically loss of resource in those areas of production added up to about just under 700 million tons of copper metal running up to 2010. And that the resources plus production was about 3,145 million tons of copper metal. And I've updated that with USGS figures to take us up to the end of 2018. So where it stands now is that cumulative production is at about 725 million tons of copper metal. And what we have left to us through expansions or through unexploited resources of known ore bodies and through ore bodies that haven't opened up yet is about 3,500 million tons of copper metal. And it's really around unlocking those unexploited tons that we wanted to understand what the challenges were. This is a really sobering slide, and I borrowed some stuff from a recent talk from Dan Wood on this, but another one from Richard Shoddy from the same, actually from a later presentation, looking at the bars there are the value of discoveries that have been made since 1950, and the red line there is exploration expenditure. And if you follow that exploration expenditure back, it's a little bit like, the defibrillator where you've applied a jolt of investment into exploration, and there's been an associated increase in discoveries. And the last jolt that we applied was the biggest one, and the patient didn't register a heartbeat, basically. So from 2007 to 2016, as somebody who spent their whole career in exploration, I'm proud to say that we spent $35 billion on copper exploration, and we found $17 billion worth of copper. So don't applaud, it's okay. So that really casts in a pretty stark light what the challenge is for us. And obviously there's a lot of work going on trying to understand why, why exploration isn't as effective as it was before. Obviously, there are some challenges around the fact that the Earth is finite. It's getting more challenging to get into different areas. The exploration is more challenging from a technical point of view, but that's where we are. So it really shows that we're not going to replace our copper as it stands now through exploration, and the same thing applies to a whole range of other commodities. This is from the Yale group, El-Shkaki et al., Tom Gradel's group, looking at supply and recycling and demand for a whole range of different commodities. And this happens to be zinc in this case, and he's just looking at a number of different scenarios depending on whether it's the equitable world there's a whole bunch of, there's 4 different scenarios there, and 4 different associated scenarios for returns from recycling. And the main message out of this graph is that primary supply changes depending on those scenarios, and recycling also changes depending on those scenarios, but it's very, very low compared to primary supply, and it's unlikely, again, to provide much, to provide enough for our future needs. And this is just another graph from the same paper, basically showing time out to 2050, and this gray bar here is resources to mid-century. That's kind of the bar where everything runs out, and these are actually demand curves. So zinc, according to this analysis, is scheduled to run out around 2035. Lead soon after. Copper soon after that. And nickel, iron, aluminium, manganese, and everything, we've got a little bit longer. And also we have a little bit longer because I think they're using USGS figures that aren't really comprehensive. But we're in a serious situation for some commodities. And it's actually made worse by the fact that when you look at all these analyses, assumption 1 in all these analyses is we're going to get it all. So they've gone to the USGS and they've said, great, there's X tons of copper metal available, so we'll just put that into our future supply on the assumption that in an orderly way we're going to go up to Pebble and we're going to produce the 35 million tons of copper metal from Pebble in Alaska, even though it's been blocked even under Donald Trump. So there are some assumptions there that are clearly subject to challenge. So, really to summarize that, and this is a thing that probably some of you have seen already, the supply of the future is really going to come from these 3 things: known ore bodies, new discoveries, recycling, plus these complex ore bodies, undeveloped ore bodies or undeveloped resources associated with existing ore bodies that are challenged due to grade problems. I don't think that one actually has a grade problem. I think we're okay on that one. Social challenges. And this is actually a picture from a town next to a project I was involved in that I'm going to present as a case study as part of this, as well as the environmental challenges of the type that have been cast into stark light in the last little while around tailings and water and so on. But what I wanted to do now was actually do the same thing Malcolm did last week, which was cannibalize a presentation that I gave at the Complex Ore Bodies Conference in November of last year. And there's a football team of authors here. They're really all the people who contributed to the work and analysis on this presentation. So again, I won't labor this, but so we're looking at really trying to address those the challenges around those complex ore bodies through a program that I'll go through in a little bit more detail later. But the aim of doing that is to try to understand, well, what is the mix of challenges actually faced by these deposits? And what's the relative value or impact of possible innovations? And that this little thing, you're not supposed to be able to read that. That's 2 examples of the multitude of roadmaps that have been produced in the last little while around around how we're going to improve mineral recovery and improve mining and mineral processing in the future. So I think people might look at things like this and go, oh, great, that's what we need, another roadmap. But the aim in this case was to say, well, to try to actually analyze what the challenges are and develop a roadmap in response to the results of that analysis. And again, a lot of these will be familiar to all of you. So this is just the Wood-Mac supply-demand curve for copper. I think there've probably been an iteration or so of it out since then, but basically we're due to go into deficit. Copper demand's at around 20 million tons per year now. Probably by 2050 it'll be up around 30. I saw one of these visual capitalist infographics where they said, we've produced, the amount of copper we produced since the beginning of time is going to be produced again in the next 25 years. And copper grades are going down, and copper resources are getting more complex, and this is just an example of that. It's just arsenic in concentrates from 2010 in the red lines and 2016 in the blue lines. This is from a tech paper talking about their technique for dealing with that. And so one question you might ask is, can a simple price rise unlock complex copper ore bodies? So can we address these grades and these complexities just by having the copper price go up? Of course, that doesn't really do us much good because we can't control the copper price. But what we can control, we've actually done a very good job of, and that is we can control the cost of production. And despite the fact that people, probably not people in this room, but people in the general world view the mining industry as a group of dinosaurs, when you look at the range of innovations, and this is another Richard Shoddy diagram, that have been applied to copper or any other commodity you could mention in order to reduce the costs associated with production of that commodity, we've been enormously successful in making progressively lower and lower grade ore bodies economic. So probably a better question to ask from the point of view of people who are trying to come up with ways to produce from challenging ore bodies is, can continued cost reduction unlock complex ore bodies? And so that's really what I'm going to try to develop now. And what I'm looking at, or what I'm going to present, some of you will have seen it already, is a database of undeveloped copper deposits. So this is from the S&P Market Intelligence database, and pretty much established through going through it, comparing it to a lot of the published databases out there, that it's comprehensive. In fact, we put out a paper where some of the other database gurus, of which there are a few, came back and said, oh, this database isn't comprehensive. And I said, well, and we actually went through it and said, well, our database has actually got more deposits in it than our deposit. Ours has got more than yours, so there you go. So there's no problem. This is a pretty comprehensive database of what remains in terms of known resources, in terms of their tonnage and grade. So the size of the circle is the tonnage, and the color is the grade. And this is just from a USGS publication looking at future copper supply. Interestingly, the USGS feels that there is no copper in Australia, which I felt like sending him a little memo about Olympic Dam and Mount Isa. But anyway, we'll leave that to the side. The only copper deposit in Australia is Cadia, apparently. Basically what we're looking at here is two different settings for the main sources of copper in the world. One is the porphyry belts that are shown mainly in these colors in through here, the Southeast Asia, the Tethyan belt, and up into the Alps over through here, and of course the orogenic belts through Western North America and Western South America, as well as the older sort of intercratonic, more rift settings like Mount Isa, like the Central African Copper Belt, and like the Mid-Continent Rift in the US. So those are really the two main sources. And we use the S&P database to try to pull apart some of the characteristics of these deposits. And the S&P is one of a number of different databases that mainly, it's designed for investors and companies to look at location, size, grade, economics, production, breakdown of costs. You go to the S&P database and pull out what different operations are spending on electricity, on labor, on everything. And as everyone in UQ has a login for this database. So it's well worthwhile accessing it. But it also has a whole series of long text fields that aren't really, that don't have authority tables associated with them. They're just summaries of public filings from companies. And so we developed, one of the things we did was develop a series of keyword searches from those long text fields, trying to tease out the occurrence of keywords that might indicate the presence of, or the degree to which social, legal, permitting, deleterious elements, arsenic in the case of copper, but it might be cyanide in the case of gold. If there's lots of mentions of that, then it might link back to a social issue. And then external data sources that are freely and globally available. So things like water stress, seismicity, biodiversity for different species, infrastructure. And actually the infrastructure one is worth highlighting because that's, in contrast to the other ones, that's actually produced by Grant Valentine, and that's why his name was on the start of this. Grant took and has presented this before, he took a database of power plants around the world and calculated basically an energy density for the whole world, watts per square meter. And it was really a lifesaver for us because there's no other simple way to assess infrastructure, and it seemed like a pretty good proxy. And we produced a whole series of, I guess, portrayals of the relationship then between the technical characteristics of these ore bodies and their ESG, environment, social governance characteristics, if you might want to call it that. So in this case, the aqueduct water risk database, which I'm showing up here, against a cascade diagram of tons in this direction, copper equivalent grade over here, and it's been truncated to 4. You'll see in some later ones that it hasn't been truncated for the DRC deposits, and then the different colors from the reds being high water risk down to yellows being lower water risk. And that's the Aqueduct Database actually produces a mining water risk index, which we accepted. And tailings risk, so we took a global terrain ruggedness index plus a flood incidence index plus a global seismicity index and developed a proxy that would then allow us to identify the areas that are probably more likely to have problems in the development of a tailings dam. So the darker blues here portray that. And this is the whole set of proxies diagram that Eleanor Leb, who did a lot of work on this as well, developed, just looking at these 12 different criteria and what we use to build those proxies. I'm not going to propose to go through them all now. That'd be kind of boring. But here's a 12 graph portrayal of tons grade that hasn't been truncated. So we go up to 10% copper over here for the highest grade DRC deposit. And the different color coding is around, in this case, grade risk, where it's obviously lower at the higher grade end, infrastructure risk, where the darker colors are higher risk and the paler colors are lower risk, and so on. So this is one way to portray that information. It's okay for an overview, but it's hard to look at actually the relationship between different deposits and for specific deposits. So what we then went to was this sort of risk matrix view, and we're looking here at the top 40 deposits, top 40 copper deposits in terms of tons on the planet or in that database, and a color scale from red being high risk to moderate, or to green being low risk, for all these different criteria for the different deposits. And again, I'm not going to propose to go through all the different deposits here. I'll come back to a case study where I actually look at something that I do know, a project I do know a lot about, and look at how it came out in the database. But I guess what you can see is that for most of these deposits, they're not subject to just one single risk. They've got a whole series of risks to one extent or another. And being a geologist, I like to plot things like a drill hole. So I also said, well, let's drill through the billion tons of copper metal from the lowest grade, so highest grade risk on the left-hand side, over to the highest grade and lowest grade risk over here, and just look at how how those things correlate. And again, I'm not going to go through it all, but there are some deposits clearly where some of the correlations you would expect are definitely there, like poverty, community, legal, permitting. Or over here, you may have guessed that this is some of the big deposits in the Central African Copper Belt, where variability, which is basically the number of different copper metals and the number of different zones are there, water, biodiversity, poverty, and so on are all serious risks. So the other thing that we did was to then say, well, what's the implication of all this for what we might do or how we might think about all these things? And what we then did was say, well, for all these risks, let's divide them on the basis of price sensitivity. So obviously, for grade, if grade, or you could say price and or cost sensitivity. So if the grade goes, if the copper price goes up or your costs go down, then obviously copper grade's gonna be less of a risk. So direct correlation, no problem there. And if you say, okay, well, how much of that billion tons of copper metal has only copper grade as a risk, and it's about 3% of the database. And then if you say, well, there's another set of risks that are indirectly price sensitive, and I think there's some of the things that you talked about last week, Malcolm, which was around things that you can alleviate by spending more money at the project scale or by doing things differently. So for example, if water's a problem in a project at 5,000 meters in the Andes somewhere, rather than trying to pump from an aquifer for which there's competition, you can build a desalination plant and a pipeline, and it's going to cost you more money, but you've alleviated that risk. Same thing for infrastructure. When we've seen presentations here on Freda River where if you spend the money to build the tailings dam with commingled, that has hydropower and commingled waste and tailings, it's going to cost you a lot of money. But if the copper price is high enough, then your project can potentially bear it. And if it's a choice then between getting into production and not getting into production, then you can deal with that. And if you take the projects that only have directly and indirectly price sensitive risks, that gets you up to about 25% of the database. The rest of them all have at least one of these they're not price insensitive really, but less price sensitive risks around legal challenges. So I don't think you could do anything in terms of copper price or changing the project, changing the plan for the project to put Reko Diq in Pakistan into production tomorrow because it's subject to a legal challenge. And the same question might be applied to, again, a mine like Pebble, where there are serious environmental challenges that may be circumvented by a radical change, but may not be. But these challenges are much less price sensitive, and that takes us up to about that covers the remaining 75% of the data set. So we're not saying that they're all these projects are all held back, these remaining ones are all held back only by social challenges, and we don't actually know the extent to which those social challenges are important, but that at least one of them exists in those projects. And we've also looked at risks by region. So I've got these little spider diagrams that I've divided up for the Earth and for Oceania, of course. The interesting thing about Oceania is that compared to a lot of them, we've got risks in everything. Basically, because that includes Papua New Guinea, Pacific Islands, Australia, New Zealand. So there are really risks. Each one of the different sort of spider webs in there is an individual project, but really they add up to quite a solid wagon wheel of risks. Whereas for different regions, you can pick out risks that seem to be more prevalent, and the ones that spring to mind, for example, are grade and tailings and variability in Chile, let's say, infrastructure, permitting, biodiversity in Central Africa, and on the list goes. Permitting and grade very much in Canada and the U.S. And we've done some other things. I don't know if I never know if this is going to work, but we'll see. We've on our website, if you're interested in having a play, you can look at all these risks. So this is actually sitting up there on the SMI website where you can just go through and say, okay, well, what's the range of challenges for all these things? And if you want to go down and look at, there's a little pop-up for what the actual deposit is. So just thought I'd point that out anyway, if anybody's interested. Now, how the hell do I get out of this? My face is in the way. I think it's going to be that one. Yes. Okay. So this isn't the conclusion. You'll be sad to hear maybe that this isn't the overall conclusions, just the conclusions from this bit. And that is that, you know, a simple rise in price or a drop in cost is not going to unlock that inventory. And that, you know, I already said that. There are obviously some challenges to the database, and we're continuing to develop that. We're just finishing another manuscript to submit, looking at trying to get away from these keyword searches of public filings, because particularly for, I mean, having been involved in public companies, for example, with a social challenge, if you've got a social problem, you're not going to release it in your press release. You don't release it until everything has become a disaster, basically, and then you release it. So you'll see with the case study I go through in a second, we had lots and lots of problems, but we only released those things that we judged to be material. And so that makes it difficult to get a real database. So we're trying to get away from that stuff. Inconsistency of data. You know, one of the big deposits in the copper database is a deposit called Udokan in eastern Russia, and there's very, very little information available on it. You know, you have to go dig away in PowerPoints. There's nothing in the database. So whereas some of the other ones have got huge reams of data. So this is the next steps from last November. We've basically done the first two, still probably working on the third one of those. And you know, so some of the updates, here's some of those risk matrices for a range of other commodities. One of the things that I'm in the process of doing is going back to the Yale diagram in the bottom left-hand corner of my first slide, showing all the different commodities and when they're going to hit the resources to mid-century barrier, and to analyze for each one of those how much our database suggests we're actually going to easily be able to recover from the resources we know about. And I've already seen that for some of those deposits, or for some of those commodities, a similar sort of pattern exists for copper, which is that there are significant non-technical challenges. For other ones, grade becomes an absolutely serious challenge. And the other thing that we've done is when you start looking at multiple commodities, grade and tons make an assumption about the knowledge of the person looking at the diagram. Their knowledge is what's a good copper grade? Or their knowledge is, what does 20 million tons of copper mean in relation to 6 million tons of zinc? And so what I've done here for these diagrams is that basically the color scheme is, if it's around gray, it means that the deposit is around the current mine average grade of mined deposits. So that's around the grade that we'll be able to deal with now. If it's blue, it means the grade's better. And if it's red, it means the grade's worse. So for copper, basically, once you get past about 25 years, the next 25 years is painful. The copper grades are lower. And it also allows you to go back to, what I've done here is that stacking these related to grade, I've abandoned that and done a cascade diagram in relation to different risks. And you can see that there are some risks like tailings risk that exist everywhere and slowly increase, and then other ones relating to biodiversity, arsenic, and other things where there's land as well, where there's a population of data sets or a population of deposits where you might say, well, maybe we shouldn't even worry about this stuff because it's just, it's going off scale compared to the rest of the data set. But, certainly what we wondered, and what some of you may be wondering as well, is how do these databases actually compare to reality? You know, it's all well and good to develop a series of proxies and map them out into a database, but it's another thing altogether to say, well, you know, how does that actually compare to what, you know, things that we know about? And of course, it's difficult when you're looking at projects that you don't have of which you don't have immediate knowledge, and deciding what the significance of that is. So the other thing that I presented at the Complex Ore Bodies Conference was a little case study from a project that was being developed by a company of which I was the managing director. So for this project, for about 4 years, I went to bed next to it at night and woke up next to it in the morning. It was our only major project, and so I think I knew it pretty much in and out. But there were a lot of other people that were involved in, of course, development or carrying out the work on this project, and a whole range of other people I could have mentioned in here that worked on that. So this is the same sort of diagram except for gold, where we're looking at the size of the square being the contained resource in ounces of gold, and the color of the square being grade. So we're looking at about just under 2.5 billion ounces of gold, which is 25 years or so at current production. And the project that we're looking at is called the Kastanelik project in western Turkey, just near the Dardanelles on the other side from Gallipoli. So again, it's slightly different this one, but a similar sort of matrix of risks for gold deposits, and again, this is the top 40, representing a little under half of the database. And when you look at, you know, what this is, again, those spiders of regional risk shown at a level where they're impossible to read. So I've blown up the one that I've done for Turkey and region, showing that you know, arsenic, tailings, permitting, grade, and community concerns are all significant for the assemblage of deposits covering that area. For gold, one thing that we really should be mapping is geographic variations in attitudes to cyanide, because that's a big issue for Turkey, Bulgaria, many parts of Europe, obviously. So just zooming in, there's for the Australians amongst us, there's Anzac Cove. I've been to Anzac Cove about 20 times. Everybody who came to visit wanted to go to Anzac Cove. It took about 45 minutes to get there from our project, which is sitting in here. Çanakkale is the capital of Çanakkale province. We were near a town called Lapseki, about 10 kilometers in from the coast. And nowhere near that top 40. The project is over 1 million ounces now, and with slightly better grades. They've continued to make discoveries since we left the project, but when we left the project, it was a bit of a minnow, really. It was 750,000 ounces at an okay open pit grade, but certainly not something you'd take underground. But what we did have from that was how the database treated that project. And what you can see is that there was a moderate risk for, if we follow that up, for tailings, a slightly higher risk for permitting, and that's based on the Fraser Institute Index, the ease of doing business, and so on, and also a risk quite significant risk under the community banner because of the population density and the moderate to high cropping density on the project, even though there were low social keywords. I'm going to run through these pretty quickly. It's an epithermal gold project, basically, and so they're generally pretty good from a processing and mining point of view. Nobody's offered us any prizes for the discovery. This was the subtle indication of the deposit at the surface, which was an enormous quartz vein that was full of gold. So it indicated to us that drilling the quartz vein full of gold was probably a good idea. I don't know why the company that sold it to us at a bargain basement price didn't think it was a good idea, but anyway, it's an epithermal system, and this is just a very early block model from that. But one of the main geological challenges you can see from that is that, like many epithermal systems, it's not one zone. There's a little zone here, there's another one here, there's another one here, there's another one here. They're in different orientations, they're discontinuous, grade continuity, where's the border of the vein? You drill a hole at point A, and then you move 25 meters, and the grade is different. There's big nugget effect. So there are technical challenges associated with the mineralization, but the good grade was at the surface, and so there were a lot of good things about it. So we felt that the technical challenges were enormous at the time, but when I look back in comparison to some of the others, they weren't so bad. For example, environmental challenges, if we come back to water and tailings. This is an area, you can see that there's a highland over here that's relatively uncropped, and then these big areas of cropping, a huge area of orchard, of stone fruit production, peaches and so on. And there are a number of local towns, Shahinli, Kojabashlar, Chemyurt, and they're drawing water from these highlands, including water protection areas. These red things are the veins. So our resource was based entirely on these veins up in here because we couldn't get access to this area. And so that was one challenge. This is also an area with a Mediterranean climate, so sometimes there's lots of water. There are other times there's absolutely no water. So there are dams for water mainly to be sourced for agriculture, and protection areas associated with those. We just avoided being in those zones, but water is definitely a push-button issue in this region. And seismic risk, well, Turkey is basically moving out to the west because of the fact that the Arabian Peninsula is slamming into the Asia-European bloc, and it's sort of squirting out to the west like a watermelon seed between two fingers. And it's doing that along a big fault zone in through here, and the North Anatolian fault zone in through here, which conveniently goes straight through our property. So Kostandalik, which is a tiny resource, as I've already said, that little red line in there is the seismic risk, band for Kostandalik that sits here against this larger zone. So for that reason, we actually decided to go for dry stack tailings, following the example of El Dorado, who did that in the Efemçukuru deposit to the further south in Turkey. And we did it for all the reasons that people always do that, for reducing competition for water, better stability in a high seismic zone, reducing permitting burdens, and increasing social acceptability. We could take locals, take them down to Efemçukuru and say, this is what our tailings is going to look like. You can drive on it the day after it's been laid out. So, and that project has ended up continuing to use that method. Now I'm just going to talk about the social context. And this is where I want to point out, I guess, that it is very important to consider how changes in the project have manifest in terms of their effect on the local community and the potential positive or negative effects associated with that. But it's just one piece of a very large puzzle when you look at the social context. It'd be wonderful if you only had to worry about the community, but you don't. There's a community, and then there's another community, and then there's another community, and then there's a province, and then there's a state, and there are different regulatory bodies. And they're all thinking about your project. And so a good thing that you do for one person might be a bad thing for another person. So I'm going to kind of try to go through the layers of that onion now, starting at country scale. So there's the capital, Ankara. We're over here in far western Turkey. Most of you would know that Turkey's had the same leader in different guises for the last 17 years or so. And in 2012, as part of Turkey's descent into whatever it's descended into now, there was a circular that was put out that said, from now on, in order to get a drill permit, in order to make any sort of a transaction relating to land, in order to carry out any sort of mining or opening of a mine, you have to get specific direct permission from the Prime Minister's office. And the reason was to control corruption. And I've got no doubt that the reason was to control corruption. So that really led to a whole series of projects coming to a crashing halt. Whatever drill permits you had at the time, because you have to get a permit for every single drill pad that you develop, whatever drill permits you had at the time, that was what you were going to have going forward. It's actually opened out again now, But at the time, it was a real challenge for us. And then if you move into Çanakkale province, which sits in through here, Çanakkale province is part of the, when you look at election results from Turkey, there's this sort of Anatolian heartland, which is very, very socially conservative, votes very strongly for the current ruling party. And then there's the western edge of Turkey, which is much more socially progressive, tends to be more, I guess, what you'd call PLUs, people like us. And they're much less interested in having a big project that uses a whole lot of cyanide in their backyard. And so there were a whole series of push-button issues at a provincial level that impacted on our project around cyanide, active NGOs, the need to get what was called a workplace permit, which by law you're supposed to give within 5 days of completing environmental impact assessment. But in reality, for some of the other developers in the region, they'd been waiting years to get that permit. General opposition to mining, because Çanakkale itself is a university town and a public service town. And it also is the home of, the Çanakkale province is the home of Troy. And so there were actually legal challenges to our environmental impact assessment that marred us in a long process that delayed development of the project. And then if you come down to the area, we were in the municipality of Lapseki. And it's at this level that you start to list both positives and negatives. So everybody was interested in employment. They were interested in being related to procurement opportunities, improvements in infrastructure, but obviously starting to be also concerned about water contamination, cyanide, traffic relating to trucks and so on. And of course, the other thing is that Lapseki used to be called Lampsakos, and this is a coin that was minted in Lampsakos in 394, somewhere between 394 and 330 BC. Probably gold that came from our Kastanlik project, because there were very, very old workings on the project. So it's an area that also has some archaeological values. And then if we come down to nearby villages, so the closest one was this village of Shahinli, which means place of the falcon, as far as I understand. There's the actual project as of Google Earth. And again, there's a mixture in here, and I'm not going to go through them all, of positives and negatives that we were dealing with. But some of these photos are worth pointing out. At one point, and this postdates our involvement, but we also had a similar event. Some of the areas from which, in the course of a drill program, some of the areas in which we were drilling, obviously drill muds got into the water that they were sourcing for their village. So that's a bottle of the water that they were receiving at the village. And you can imagine people were just over the moon about that. And here's actually in this case, this is a protest from local villagers trying to stop environmental activists from Çanakkale coming and disrupting a public meeting. So it was actually in favor of mining rather than against mining. And then if you go down to the local area, this is right on the project. This is a sort of a perspective view of the project. You can actually see some of the drill pads and one of the main veins here, the K3 vein. Jem Ujair was our manager on that project. But a lot of the same sort of thing relating to positive and negative concerns. But then we also had competing people working on other things in the area. You can get a license for treasure hunting in Turkey, as you could well imagine from the depth of history in the place. So we actually had people that had tenements for treasure hunting in the middle of in the middle of the area we were carrying out exploration. And there were also people that were doing scoping for wind farms. It's an area where there are a lot of wind farms. It's a very windy place, and they get a lot of power from wind farms. As Joe Hockey would have said, they were terribly unsightly, but I thought they were okay. And competing companies from adjacent licenses. And it was an area where people would take their goats and sheep and that sort of thing, so there was competing land use. So all of these things added up to different challenges at different scales. And all this was happening against an interesting backdrop, which was that from 2011 to 2014, gold stocks in general, this is just the All Ordinaries Gold Index, lost between 75 and 80% of their value. So gold was not the flavor of the month over that same sort of time. And so the end result of all that was that we were stymied, we had no money, we couldn't get around the social, environmental, and governance challenges that were stopping the project from being developed, and we sold it to a Turkish company who had no such problems, and it's now in production. It's been in production for a year or so. But I guess what I wanted to show this was to say, well, the case study certainly confirms the complex interplay of technical, environment, social governance risks that we identified in the regional database. What I would say is that the global study underestimated the ESG risk of the project. So, and I think that's likely to be a common occurrence, particularly when the index is reliant on public filings around companies. But I guess the other point to make is that the level of ESG risk is also variable depending on who you're applying it to. It was very high ESG risk for us, but it was very low ESG risk for one of Turkey's largest arms manufacturers. So, but some of the key issues I've just listed there, and I think I've gone over them. So I guess what I tried to show there was a case study of an actual example and how it relates to that database. There's the project as of middle of last year. All those pits, including pits covering the water protection areas, the waste rock facility over here, the dry stack tailings, the camp. So that covers that. What I want to do in the little bit of time I have left now is to just go over a bit of a summary of some of a broader overview of some of the work that is being carried out outside the work that I'm doing in the complex ore bodies program. And we really divided it, as I showed you at the start, into, aside from the complex ore bodies database side of things, into 4 different areas. So understanding social complexity relating to the impacts of mining, dealing with environmental footprint and environmental barriers, techniques and technologies that are focused on addressing some of the footprint-related issues that we've identified, and dealing with, trying to make inroads in the sort of variability and flexibility nexus that is one way forward, I think, for deposits. So. We've already talked about this, so I won't spend too much time talking about that. But and so that's a theme that sort of sits over top of those, the understanding complex ore bodies. But what I did want to point out, that in addition to the work we're doing, we've also supported Laura Saunter from Earth Sciences to do a work focusing specifically on mining biodiversity. The interesting thing that came out of that is that when you actually, so they actually looked at a basket of more of the renewable economy metals, like lithium, cobalt, indium, graphite, and so on, and looked at their relation to key biodiversity areas and human development and last of the wild databases and other sort of more Earth-related biodiversity databases. And the one of the results from that study was that the transition to the renewable economy is going to place more stress on those sorts of areas than the traditional coal, iron ore type developments that have been around for a long time. So we've been working with the School of Earth Sciences on this. We've also had some involvement with the UQ Business School, and S&P Global have provided us some in-kind support for this part of the project. And then when you look at social footprints in data, and it's really around addressing this issue we have in terms of trying to improve our practice, the industry practice in the social area. So the CSRM people have been working with Rio Tinto on a strategic review of communities and social performance that has been initially applied to Rio Tinto, but then we've used our complex ore bodies data or money to go out and do a much broader benchmarking study of how companies themselves feel that they're addressing social issues and how they feel that they can improve in that area. and also looking at the relationship between large-scale mining and artisanal scale mining that's coming up again and again as a challenge. And actually, we listened to a very good presentation from Junyu yesterday on the work that we're doing with the Center for Coal Seam Gas on trying to apply their Boomtown toolkit. And under this banner also sits the work that Malcolm presented last week. You know, trying to come up with a way to say, if we've got 5 different project alternatives, which one has the best, which one is associated with the most favorable social outcomes, rather than just optimizing on the basis of making the maximum amount of money and leaving the social outcomes behind. And I think that understanding that in a number of different ways is a really important thing to do. So that's another area that we're working. Yes, so the Center for Coal Seam Gas sits behind that little diagram, but we're working with Panost on large-scale mining, artisanal scale mining, as I said, Rio Tinto. The other one. And then from the point of view of projects that are aimed at trying to reduce footprints, because I think one of our main hopes, and the only way that we can, I think the only way that we can deal with the more price insensitive risks associated with deposits is to remove some of the things that are making people unhappy about the projects. And that's around getting rid of deleterious elements, getting rid of tailings risk, stopping competition for water, dust, all of the things that you presented so well last week. Or not having an open pit altogether. So we have a project working with the School of Chemistry and Molecular Bioscience on in situ recovery, innovative ways to do that. The coarse particle research that Kim and her team are running, and also we're trying to get going on removal of deleterious elements, or continue the work that's already been done here for a while on ways to remove deleterious elements from copper concentrates and other concentrates. And we're working with a whole series of industry partners, and I guess you know, very strong support with a UQ partner on that project. And then on the variability, flexibility side, obviously I haven't done my animation too well. So we've had a project working with Glencore, looking at trying to come up with ways to better document variability in deposits. Susanna has been involved in a work looking at novel reagents for flotation. There are a range of other projects in this area that are under development, but our partners on that have been, we've also been working with with IT and electrical engineering on some of the challenges relating to this project. I should have chemical engineering in here as well, because I know that you've been interacting with them, and these are some of the external sponsors that are involved with it. And then on the energy and efficiency side of things, of course, the high voltage pulse work that's been presented elsewhere, and coarse particle processing that I already talked about. So that's not all the projects, but it's an overview of some of the projects that we're carrying out as part of the broader complex ore bodies program. And I don't have a sort of grandiose set of conclusions. We're 15 months into the program. Monetarily, I guess, in terms of programs, we had some objectives for the program in terms of bringing in external sponsorship that we've met, in terms of interaction within UQ and with industry that we've met. But when you come back and look at the results of the work that we've done so far and the stuff that I've presented today, I think there are sort of 2 broad groups of deposits to consider. One is the mines that are already in operation, where the new resources might come from extensions. And you know, the challenges there are mostly technical, but I think we're starting to see more and more indications of the fact that people aren't just being given carte blanche to go out and do a double expansion of their deposit to get resources that they already know about. That the sort of ESG challenges that we're seeing for undeveloped ore bodies are also going to apply to deposits that are already permitted to be mining. But what I would say about mines already in operation, and all the roadmaps that I mentioned before, is that this is an area where you'd say it's already the subject of intense global research investment, And what I tried to show with Richard Shoddy's diagram on cost per ton to produce copper, it's also been the subject of great success by groups like the one in this building, in terms of coming up with ways to reduce costs on existing operations. So it's an area that we're intentionally not focusing on as part of the Complex Ore Bodies program, because it's already really well addressed in existing research initiatives and well supported by other initiatives. But then when we come to ore bodies and deposits not yet in production, there's a variable mix, but a large amount of environment, social governance challenges, where the key areas to address are, community and social performance, in terms of how companies interact with communities, and there's a lot of work going on in that area by the CSRM, but also this whole concept that I already talked about around trying to reduce the footprints of projects. And that's an area where I think that every group in the SMI and a number of groups outside the SMI have a great role to play in coming up with solutions that remove the impediments that are creating those environment, social, and governance challenges. And I think this is an area that when we look worldwide has had relatively little research investment. So it's a very fruitful area of research, I think. And the work that we've done on the database has certainly confirmed that the importance, therefore, of bringing the sort of team that we have to do that, and I think provide a strong support for the program focus. So that covers what I wanted to say. Thanks very much for your attention.